We are recording and we are ready to resume with our first afternoon session. Thanks to Lorenzo Mauro, that will be our chairman for this session. And thanks to Artur, that will be our first speaker. So Lorenzo, the floor is yours. Thank you.
Thank you, Daniele. Thank you very much, and welcome everybody to the last but not least session of this workshop, which is devoted to quantum hardware and software providers. So I have the pleasure to introduce you Arturo Stabrawa, which is the Business and Technology Development Manager at ORCA. Artur, thank you very much for being here today. And whenever you're ready, you can start your talk.
Perfect. Thank you very much. First of all, thank you for inviting me and giving me the opportunity to speak here. That's a real honor for me. Thank you for the introduction. Yes, I'm representing company ORCA Computing. That is a London-based startup that spun out from Oxford University. And we are a company that's building quantum computers based on photons, on single photons. So let me just give you a brief introduction to our technology, what we are doing. So as you know, the most trending technologies that are out there for quantum computing are superconducting, trapped ions, neutral atoms, and a few more. Photonics is probably one of the newest additions to the market when it comes to availability of hardware for end users. What's the greatest benefit of photons is that when you think about scaling and interconnecting different computing nodes, most companies usually turn their attention to photons because they're great carriers of quantum information, right? They're room temperature based, they can transfer the information over long distances, they preserve that quantum information. Photons don't really interact with the matter unless we really want them to. So the photons are great means of quantum communication, right? But on the other hand, they're also great at doing quantum computation. So if you can use the same platform for computation and communication, that seemed very reasonable to our company, a very reasonable route to pursue. That's what we do. Our mission as a company is to build fault-tolerant quantum computer with photons, as simple as that. You might argue that the photons haven't yet really matured as quantum technology for quantum computation. However, you might recall that last year, a Chinese group actually proved or claimed quantum supremacy using photonic platform. That was a really amazing scientific achievement. That was a really great paper published in Science last year. So ORCA is doing something similar in a way that we're also using photons and photonics to build our platform, but we took a little bit different angle on the approach. So we're not striving to reach amazing scientific breakthroughs. What we are doing is we are trying to provide end users with something usable with very near-term utility that they can play around with, they can test, validate, they can get to know with the technology. We're basically bringing the near-term noisy technology to the end user's fingertips. And what you can see on the picture on the right is our quantum processor based on fiber optics. It's programmable, compact, very reliable, built from off-the-shelf components. And it fits in the standard rack shelf unit that you can have in your data center or in your lab, which is really amazing. And how we managed to do that, we basically, we have a patented approach that uses our quantum memory technology, which allows us to move from spatial multiplexing of single photons, which requires you to have a lot of photon sources, a lot of detectors, a lot of routes, a lot of equipment overhead, and we took that and we moved to time domain. I'll let you know what that means in just a second, but basically it means that we reduced the component overhead, and we managed to do the same with way fewer components, so way fewer things that can break, with much lower cost and with a much smaller footprint, energy requirements, and so on and so on. As I said, this technology is based on our patented approach and our core technology, which is quantum memory that allows you to buffer operations in time domain. The very most basic, very most simple approach to that architecture is presented on the picture here. That's actually what resides inside our first PT-1 prototype device that we already have working in our lab in London. And the working principle is that you take single photons in a fiber that are separated by some time. So each photon is allocated in a separate time bin, and you put them through an interferometer, which so you have a fiber loop in here with a coupler with a splitting ratio that can be tuned with this parameter theta. So each photon, when it comes to this junction or this coupler, can have a different coupling ratio. So with some probability, it will go inside the fiber loop or go through. If it goes into the fiber loop, then the wave function of the photon that goes into the fiber loop will then interfere with the photon from the next time bin, which allows us, as I said, to do the interferometry in time domain. And classically, simulating single loop device is relatively doable on a personal laptop. We actually have a software that can do that very efficiently with many photons and can run very nice algorithms. But when you when you add consecutive another loop in series and another and so on, then even with two loops, this becomes a really hard problem to simulate classically. And this is where we believe very first sort of advantage lies, or very first utility lies. So this is something that is very hard to simulate classically, but in terms of building a hardware, is as simple as just splicing two fibers together. So that's a really amazing approach. That's something that can bring really amazing results really soon. And we will be releasing the hardware prototype in early 2022, so early next year. And we're very anxious to see what sort of algorithms and use cases we will be able to address with that. But so far, with very first implementation of the device with a single loop, with a few photons in the fiber, we already managed to do some really interesting science and some really interesting experiments on our device. Because this device is basically a boson sampler, it's really useful for machine learning experiments and machine learning applications. Which means we can do AI, we can do optimization, classification problems, which I will go into in just a moment. But also we have a very clear roadmap where we want to take that device. So basically, we have this small box with a few additional boxes that are laser source detectors, control electronics, and so on and so on. It all fits in a rack shelf unit, but we intend to release a series of upgrades to those components that will still maintain the overall architecture for end user, but will enhance capabilities of the system, of the device. And after a few iterations within probably next 2 years, we will be able to use that conceptually simple device to generate so-called resource states. Those resource states are states of entangled FU photons that can be used efficiently for measurement-based quantum computing paradigm, which is complementary to gate-based paradigm. So here, I just told you that the strategy of the company and the long-term roadmap is to take those simple devices, upgrade them, and then move towards measurement-based quantum computing paradigm using single photons and and resource states to eventually reach fault-tolerant universal quantum computation using room temperature, off-the-shelf components that can be basically placed in a standard data center without any additional overheads in terms of dilution refrigerators or ultra-high vacuum systems and so on. So this is a very promising roadmap, and we are working tirelessly to reach that goal. So how does the current system work in terms of software that we can run on it and some applications? So we have tried and we have built a software development kit and a very efficient simulator of our system that can do already some variational algorithms, and tried to figure out how we can put that into action into some specific use cases. So the whole system, as I said, as I mentioned, we have those tunable parameters of those fiber loops called theta. Those are physical parameters that can be tuned. So when we put our system into a loop, learning loop for a variational algorithm, you tune those parameters, you set some values of those parameters, you look at the photon number probability distribution at the output of the system, you do classical computation, which lets you infer cost function that then tunes and updates the theta parameters, physical parameters of the system, and closes the loop. And then this is the way you can train your first very basic, very simple algorithms and use that for some applications. The very first ones that we looked into are in quantum chemistry, classification, optimization, generative modeling, and so on. And it's a really amazing test bed for very early algorithms and very early interaction with actual quantum computation. And our software development kit has been developed in Python. It's designed in a way that you don't really need to be a quantum scientist to run it. It's been developed by machine learning experts. So if you want to take it for a spin, you just because it's integratable with standard machine learning libraries like PyTorch, for example. It's very easy to use for any given machine learning expert. You just program it as you would train any machine learning algorithm, and our library basically takes care of all the simulation, all the quantum stuff that goes underneath in the most basic layer. Here is one of the applications that I think is particularly interesting in our case. So we developed, as I mentioned, the system is particularly suitable for machine learning and even more suitable for a QUBO problem. So for example, we took a portfolio optimization problem where we had, in this case, I believe 20 different stocks, 20 different companies that had risks and some return on the profits. And then we tried to optimize what is the best proportion of each stock for any given risk that will maximize your return on the investment. And if you look at the graph, so in order to tackle that approach, we needed to map that problem into a Cubo language. And that is one thing that we did. We actually developed a proprietary problem mapping technique, which very efficiently managed to map that problem onto the Cubo. And then we ran our Cubo solver on our software simulator and compared those results to a random portfolio spread. So we took thousands of points, of random points, and plotted them on this graph against 3 points that were found with our software. And as you can see, our points lie on the most efficient borderline of the whole problem. So for each given risk, we managed to obtain the maximum annual return on the investment, which means you only needed to run the system a few times instead of thousands times to actually reach the most optimal value, which is very promising and I think allows you to do some sort of sensible and actually useful computation with much fewer overhead and much fewer resources than if you would use a classical device. Just to be sure, I'm not claiming advantage here. I'm very far from that, but I'm just simply saying that our algorithm and our simulator coped with this problem really well. You could do that. You could do that on a classical device as well, but as I mentioned, this probably means that with implementation of our hardware, you could do that with way fewer resources. We will be soon releasing a paper on that, so look out for that, and we will have more details on those measurements very soon. The second application I would like to share with you is actually using hybrid classical quantum algorithm for image recognition. So we tried to tackle the problem of the NIST test, so handwritten digits, recognition of handwritten digits, and we found that our system works best if you treat it as a quantum layer in a classical neural network. So the architecture of this whole problem is that you have input images, you put them through a neural network that then outputs as an output from that neural network, you have beam splitter coefficients that you feed into the quantum layer, you might say, of this neural network, and then you read out the photon number distribution that you then you put into the classical computation that gives you class probabilities. And with only 4 photons in a time bin, we managed to reach accuracy of over 95% in image recognition. That means that's a really good result. And then if you add more loops or more photons, that will definitely allow you to tackle more complicated, more interesting problems. As I mentioned, again, this quantum layer here uses fewer resources than you would need to use if you used a classical neural network in this place, which is again a very promising result. So because we started to look into those quantum classical hybrid algorithms and quantum classical different layers of a whole task or application, we realized that there is a need for a hybrid to make our system good enough to be part of a hybrid, much bigger hybrid quantum classical data center system. And I'm very happy to say that recently we were awarded a over £11 million Innovate UK grant to help in building a data center of the future. So ORCA is coordinating a 15-partner large consortium, including very big brand names, that is tackling the problem of building a data center that includes and hosts both quantum computing equipment and quantum communications equipment, working together to bring a full capability of quantum into a data center that can then tackle hybrid quantum classical problems. And this is a very exciting for us because this will bring us and our systems even closer to end users and our customers. That's something that we'll be starting probably in January. So we're really gearing up to that task. I chased through the slides, so I will just start concluding my presentation. ORCA Computing currently has available a quantum device that's sitting in our lab. Early next year, we are planning on releasing that both as a commercial offering. If someone would like to own a quantum computing system of their own in their laboratory or in their data center, they can buy one from us. On top of that, we are talking to some cloud providers that will help us host our system over cloud for remote access as well. But in the meantime, we already have a software simulators available. So that's the software development kit I showed you that helped us in working towards those two applications that I highlighted. This one is available upon request already, and also if someone would like to host that software in their data center and then provide access to it for their end users, it's also available on commercial basis. But this is something we really encourage you to reach out to us and talk to if you're interested in any way in any form of collaboration, be it hardware or software or some projects. And the future outlook that I didn't talk too much about is that our platform, this early PT platform and the technology that we're developing right now is already useful, but will also constitute a backbone of the future measurement-based quantum computing that ORCA is developing. And if you have any questions and would like to learn a little bit more about us, I'm very happy to answer all your questions. Just reach out to me at artur@orcacomputing.com, and I'll be very happy to continue some discussions with you after the presentation. And this is the team behind this whole progress. That's the team from ORCA, spanning currently across 2 continents and 3 countries. We have offices in London, but we also have offices in Canada and in Poland. And we are very happy that our technology is already reaching the market and helping customers to progress their experience with quantum technologies. And with that, I would like to conclude my presentation. I'm very happy to take any questions. Thank you.
Thank you very much, Artur, for your very interesting talk. So let me check if you have any question on the chat. Meanwhile, I recall that you can ask a question by just raising your hand. And in the meanwhile, we are waiting for questions. I would like to ask you something. In particular, I was interested in the Kubo problems that you are able to solve. I mean, do you have any particular constraint on these kind of problems, like in the D-Wave hardwares, where you have, for instance, topological restraints, or are you able to implement, say, any Kubo problem? And if it is the case, what is the biggest Kubo problem that you can map actually today on your computers?
Yes, so I think the answer is resides here, I guess, because our system is not a standalone quantum computer. You actually can interface it with hardware with classical layers, like in neural networks, for example, or any other preparatory calculation. We are much more universal than just simple Kubo problems. That's first of all. There are some constraints, though. For example, we recently tried to tackle a traveling salesman problem, and because of the fact that some of the results or some of the answers that we get are not feasible, there are some boundary conditions. Sorry, I'm not an expert on that. I might need to refer to colleagues of mine, but that problem basically doesn't map very well onto our system and onto Kubo that we can realize with our problem. Traveling salesman is a very bad problem for us. However, for example, a knapsack problem, which I believe is very difficult on D-Wave, in our case gave really amazing results. But that's very fresh. We just started doing that this week. So we have very preliminary results from direct calculation and our system. And we're not claiming to be experts on D-Wave. But we obtained much better results than on a D-Wave simulator for a knapsack problem. So this is slightly different platform to D-Wave, I'd say, with different algorithms, and we're still trying to figure out what problems are the best that we can solve. And in terms of the size of the problem, again. Here I showed a MNIST test, which is already quite interesting. That's 58 by 58 pixel black and white pictures that are recognized with only 4 photons. You can imagine in our simulator, we can go up to, I think, 200 photons for a single loop right now. That's a simulator, which can address really complicated problems, much more complicated problems. But the simulator doesn't really simulate problems where you have 2 consecutive loops, fiber loops in a system, because that's a problem really hard to simulate. So we won't really know what's the size of the problem that we can address until we build the hardware and test it. And that's something we're doing right now, which should be ready early next year.
Thank you very much. It was a very clear answer. So if we don't have any question from the chat, we'll thanks Artur for joining us today. Thank you very much.
Thank you very much. It was really a pleasure to talk to you. Take care.
Thank you.